Hello, Gagan sir, am audible?
Yes, sir, you are audible.
Oh, thank you, sir. Uh, Participants, let's us move on the next session. And the topic of this next session is case studies of additive manufacturing in industry. And the expert of this session will be Mr. Gagandeep Singh. Mr. Gagandeep Singh currently working at Minda Corporation Limited as assistant manager in product design department. He has done his BTech in mechanical engineering and MTech in production engineering. He has a experience of 15-year industry. In his current job, uh, in his current job role, he is dealing with the design of mechatronic security system like EHL, key job, MHL, fuel tank caps, and side cover locks for OEs like Bajaj, Mahindra, and IKM. I would like to thank Mr. Gagandeep Singh for joining us this FDP, and I request you, can you start? Over to you, sir.
Uh, Thank you, Dr. Guru Page, for your
Thank you,
kind
sir. Thank
words.
you.
Let me share my screen first.
Yes, sir. Yes, sir.
My screen is visible to you.
No, sir. I think it's taking time.
Okay. Now,
Still not visible, Gaganji.
okay. Now it is visible.
Yeah,
Yes,
it's visible.
yes, sir.
Very much, very clear.
First of all, as Dr. Guru Page introduced myself, before starting, let me introduce myself as well. I am Gagandeep Singh, and I have done my BTech in mechanical engineering and MTech in production engineering. Total, I am having 15 years of experience, out of which 6 years of industrial experience and 9 years of teaching experience. Currently, I'm associated with Minda Corporation Limited as assistant manager in product design department. Here, I am responsible for designing of two-wheeler security systems, including mechanical steering locks, electronic steering locks, fuel tank caps, side cover locks, seat locks for customers like Bajaj, KTM, IKM, Triumph motorcycles. So about Spark Minda, I must tell you that we are having total 28 manufacturing plants across India and overseas, that is in Indonesia, Vietnam, Japan, etc. So total we are having 9 industrial partnerships like with renowned companies like Silica, Vast, and last year our group is having turnover of 4,651 CR. So these are the product range. Currently, we are dealing with the vast product range and offering security solutions in advanced electronic parts, mechatronic parts, electronic distribution system, aftermarket
Sir,
division.
sorry to interrupt you. Slides are not moving.
Uh, okay.
Dr. Gurpej, slides are not moving.
Yes, it's visible.
So these are the different products that we are offering, and we are supplying to different OEs. So in mechatronics, we are dealing with two-wheeler, four-wheeler security systems and starter motor alternated system, sunroof and power lift gates. In advanced electronics, we are offering driver informative system, ADAS sensors, smart electronics, and EV mobilities. And in electrical distribution systems, we are dealing with two-wheeler, three-wheeler, four-wheeler, and EV wiring harnesses, EV powertrains, EV bus bar chargers. So these are the various products that we are offering. Now these are the different customers for which we are making our components. Now, as I told you that Minda is a tier 1 proprietary supplier company, and companies like Honda, KTM, TVS, Bajaj, Suzuki, etc. directly purchased our parts for assembly in their vehicles. We are well established R&D department where we have 750 plus engineers, and Minda spends 4% of its total budget in R&D activities every year. Now talking about two-wheelers, these are the different products that we are offering to various companies like keyless entry system, key fobs, mechanical locks, die casting products, tilt sensor, high voltage wiring harness system, side stand sensors, antenna, speed sensor, DC-DC converter, temperature sensor, electronic handle locks, etc. Now in four-wheeler segment, we are having this kind of product that like digital cluster, key fobs, antenna, electronic steering lock, sunroofs, EGT sensors, interior plastics, power lift gate system. So these are the various other products are also listed here. Now in commercial vehicles, we are having this kind of product range. So this is a little small introduction about Minda Corporation Limited. Now, as our today's topic is additive manufacturing, so we have to tell the role of additive manufacturing in industry. Now, to start, before moving to the additive manufacturing, let's talk about the product design cycle, or you can say that product development cycle that we are using in industry. So in this total, there are 7 steps. First step, there is research of market, then ideation, that is we have to generate the idea, that is after market research, we need to generate a problem for which we need to make the products. Then in third step, there is concept development and prototyping. After that, concept testing will be done, and if concept testing everything is okay in concept testing, then we can finalize the concept, and we will do the fifth step, that is engineering development and testing. In engineering development, there are a lot of activities, that is detailed design will be done in this engineering development and testing activity. Next is marketing, and then launch of the product. So let's discuss these steps one by one. So first is market research. Now, as you all know that before making a product, we need to study the market that in which we have to launch the product. If we don't know about the market, then we cannot make right products which are high selling. So in first step, we have to understand the user. So if we understand the user better, our products will be automatically better. Next is to identify the problems. That is, what are the user's pain point? So we need to identify that one. So after identifying the user needs, we have to define one problem. After problem definition, we need to gather the more information about that problem. Now, after gathering information and data to support the development of the new products. So this is in this whole activity, we completely study the market, that is which kind of requirements are there and what kind of products that we have to design. Next is ideation. Ideation means creation of an idea about from the market study. So in ideation, basically it involves the collaborative efforts involving the various kind of stakeholders known as CFT, cross-function team. In cross-function team, there are design engineers, product development and engineering teams, marketing teams, and customers. So all sit together to finalize the idea about the product. That is what will be the future roadmap. In this, we make the particular roadmap for the designing of the product. Now, ideation stage can take few days if the concept is simple, and we can decide easily what kind of product we have to make. So it can be completed in few days, or it can take several months, or it can take years as well, depending upon the complexity of the product ideas and resources available. Next is the concept development and prototyping. Now, as our topic is additive manufacturing is basically the most commonly name of the additive manufacturing is 3D printing. So, in concept development, the first stage is the preparation of CAD models. That is, whatever is in our mind, we need to draw that model on computer with the help of certain softwares like Creo, SolidWorks, CATIA, etc. So by using those softwares, we make a concept. So if we make a concept, then how our parts will look like, how our products will look like. So for that, we need to make the products through the tooling, or we need to make such arrangement, make our products parts in such a way that they can manufacture through the additive manufacturing.
Yes, sir,
I'm audible now.
audible, and your screen is EPT is also visible. Please continue.
Sorry for the network issue. So let's start about the case studies of additive manufacturing. First of all, I include a first case study from my industry, that is Minda Corporation Limited. So here we are making handle locks. So I select this topic, this product, that is ignition switch cum steering lock, which is high in weight. That is overall weight of the part is 568 grams, which leads to increase the cost of product. So we have a challenge to reduce the weight as well as to decrease the cost. So as an alternative, we do analysis, and it is observed that the main housing of the ignition switch is the major contributor for the weight. So we choose explore alternative material, and as an alternative material, we choose ADC12. That is aluminum. ADC12 is an aluminum alloy, and we use first of all we make the parts with direct metal laser sintering process. So this is the proto part that we made. So this you can see that the finish is not as smooth as required as I compared with this particular part. So this is the tooled up part, and this is the proto part. So That's why after processing is required in additive manufacturing process. So after making protopart, we do testing like log bar strength test, and it successfully meets our requirements. Then we convert that body, that housing, to aluminum ADC12, which reduce the overall weight of the switch to 384 grams, and cost of the product is reduced by 22.5%. So that is the benefit of additive manufacturing. Next case study is in from aerospace industry, that is GE Aviation. Now, as we all know that in aerospace industries, lightweight, durable, and high performance products are required. So GE Aviation utilize additive manufacturing to produce a jet fuel nozzle. Initially, the nozzle is having 18 parts, which were then 3D printed as a single part using metal powder. So this method allowed for complex internal geometries. So with the production of 3D printed nozzle, there are reduction in 25% weight and 5 times more durable and 25% less costly. So that's why you can see that additive manufacturing significantly uh, do the cost savings and improve the performance of the critical aerospace components. So similarly, in automotive, that is BMW Group, as we all know that BMW cars are costly, and they do customization as well. So for customized products, they use 3D printing. In healthcare, Organovo is the industry which is creating the liver tissues, 3D printed liver tissues, and for drug testing and for their research purpose. In customer goods, Nike use the 3D printing to manufacture to customize the shoes for the individual persons, for example, for athletes. So this is also a very good example of additive manufacturing. Next, construction company Icon is using 3D printing technology for the making of house and for making of house. So that is the role of additive manufacturing in industry. So in product design, product development life cycle, the next step is concept testing. The concept we made with the help of additive manufacturing, we have to test that concept. If the product concept is evaluated to determine whether it works as intended or not, meets our requirements or not, satisfies user needs or not. We sometimes do the prototyping, and sometimes we test the parts with the help of some other ways like FEA, finite element analysis system. For example, in case of finite element analysis, the CAD model is first slashed into converted into small particles like mesh. This is this one. Then we apply the assembly constraints, that is this housing, suppose this housing is fixed from this point and from this point, and load is applicable on this projected lever from left side and from right side. So we after on computer screen we can apply the loads on this housing, and this will show the result. The green portion shows that there is very less stress on that particular portion, but only one red area is here, that is this one, and high stress is concentrated at this point. So that means the chances of breakage of this housing is from this particular area, and rest everything is fine. So we have to remove the highly stress concentrated point. After removing stress point, we can move further for making the better design. Next is engineering development and testing. So in case of engineering development, the testing stage involves the transforming of prototype into a detailed design that meets all requirements, has been tested and can be
Sir,
manufactured.
Kindly
So
move
in
your
this,
screen, please. We are seeing your screen is not moving. Okay.
Gurpreet ji, that is the issue. I
Oh,
don't
done,
know.
done, sir. Done. Continue, please. No, it is clear.
Okay. I think there is problem when I full screen my screen. Uh, I will start by using this one. So in engineering development, we have to do the detailed design. In detailed design, first of all, we do the DFA, that is design for assembly. Next is DFM, design for manufacturing. Next is design failure mode and effect analysis and tolerance checkups. So in this way, we design the complete. Hello.
Yes, sir. Yes, sir.
Okay.
Continue, sir.
Okay. Okay, sir. Okay. So the detailed design includes the DFA, that is design for assembly. DFM means design for manufacturing. DFMEA is the design failure mode and effect analysis. And tolerance checker means we do all the calculations regarding tolerance and geometric tolerance, etc. Now let's talk about design for assembly. Design for assembly means the concept that we make on computer screen. Now we have to talk about the physical assembly of the components. So its definition is DFA is the method of designing the product for ease of assembly. That is, if we want to make this product, then how easily we can assemble all the parts. That is optimization of the part system assembly. So DFA is the tool used to assist the design teams to in design of products that will transition to productions at the minimum cost, focusing on the number of parts, handling, and ease of assembly. Now, design for manufacturing. Design for manufacturing is the method of designing for ease of manufacturing. मतलब in this case, how easily we can manufacture the part. In DFA, how easily we can assemble the part, and in DFM, how easily we can manufacture the part. In manufacturing, we have to talk about the various manufacturing methods, and in DFA, we need to minimize the parts to to save the assembly time and to for ease of assembly. Now differences in design of assembly means we need to concentrate on the assembly of the components only. That is how we can reduce the assembly time, how we can minimize the assembly operations. So that is our main focus in DFA. In DFM, our main concern is about the production cost, production complexity in the production operations. If the manufacturing operation is simple, then production cost will be less. If the manufacturing process is difficult, that is, uh, for example, we use some special purpose machines, SPMs, then overall product cost is high. So always while designing a product, always try to make the components shapes such that it can be manufactured with easy machining, not with the complex machining. Now, similarities between DFM and DFA. Both DFM and DFA seek to reduce the material, overheads, and labor cost. They both shorten the product development cycle time. Both DFM and DFA seek the utilization of standards to reduce the cost. Means DFM and DFA, this activity works simultaneously and it is used to reduce the overall development cycle time and to reduce the cost of the product. Now, if I compare DFM and DFA, then which one is more important that we have to decide first. First of all, we do the concept design, then we have to do the design for assembly, then we have to do the design for manufacturing. So if our design of part is simple, then manufacturing cost will automatically will get reduced. So design of the part is responsible for 70 to 80% of the overall cost of the product, and manufacturing method is only is responsible only for 20 to 30% of the total overall cost of the product. Now, to reduce the cost of assembly, so that means we need to focus more on DFA instead of DFM. So, to reduce the cost of assembly in DFA process, we need to calculate the design for assembly index, that is DFA index. So, in DFA index, how we can calculate that one? This is the formula to calculate DFA index, that is theoretical minimum number of parts into 3 seconds divided by estimated total assembly time. So theoretical number of parts means the net parts that we have to assemble to make a particular product into 3, that is the empirical formula. So, and divide by total assembly time. Next, by integrating parts, how we can reduce assembly time? If we suppose in our assembly we have total 20 parts, then estimate time to assemble 20 parts will be more if we have 15 parts in other assembly. So time to assemble 15 part is less as compared to time to assemble the 50 parts. So by integrating the parts, we can reduce the assembly time. Maximize ease of assembly. So next is maximize the ease of assembly. How we can make our assembly easy? We can make our assembly easy by inserting the part from top of the assembly. Now, top of assembly means first of all we put the base part, then we have to put insert the second part, then third part, then fourth part from the top. Side and bottom assembly of the part components are always negligible, neglected, are always avoidable. So next is parts self alignment. Then part does not need to be oriented. Part requires only one hand for assembly. Part requires no tools. Part is assembled in a single linear motion. So these are the various steps how we can make our assembly easy. Next is minimize the part cost. Design of part with self-locking feature, that is introduction of the self-locking features like snap fitting instead of screwing, because screwing need more time as compared to the snap fitting. Then design of parts with self-fastening features, minimize or reorientation of parts during assembly, emphasize on top-down assemblies, standardization of parts, minimum use of fasteners. So these are the various points how we can by which we can reduce the time and cost for assembly. So let's see this by example. So first of all, this is an assembly, exploded view of an assembly. Here we have different parts, that is cover. This is cover. This is set screw, base, sensor, covers, screw, bush, plastic bush, so motor. So in this now in this table, we can see that base and number, bush are 2 in numbers, motor assembly 1 in number. So total there are 19 parts. So in order to calculate DFA index, we first of all we have to remove all the screws, bushes, and other things. So theoretical count are 4. Total assembly time is 160 seconds. And then we divide theoretical number of parts into 3 divided by total assembly time. So by which we can calculate the assembly index, that is 7.3, 7.5. So assembly index should be more than 50%. So now we have to redesign, we have to rethink about this whole assembly process. And after redesigning, we just can convert the base like this, housing shape like this, motor shape like this, and only 2 screws are there. And after DFA, we reduce the total parts from 19 to 6 only. So now the assembly index is 26% in this case. So this is how our DFA works. Next step is design DFMEA. DFMEA full form is design failure mode and effect analysis. So in design failure, in failure mode and effect analysis, first of all, we have to do collect the collect and analyze to determine the cause of failure. We have to identify the failures, various kind of failures. Let's take the example of ignition lock. So in DFMEA, first we have to think that is how our product can fail. And where it is started? It is started by US military and widely used in many of the industries in various forms. So DFME is also having 10x rule. That is, if we detect the failure in the development stage, then the failure cost is only rupees 10. Secondly, it will be increased to 100 times if the failure is detected by within an incoming inspections. That is, during development stage, if we detect a failure, the cost of the failure is only 10 rupees. And during inspections, if it is detected, then cost of this failure will be 100. But if that failure is detected in the final test, that cost will be increased to 1000. Further, it is increased to 10,000 if the failure is found in the field. Suppose we are having a product, for example, we are having a ignition lock. If we think about the failure on in the design stage, then that cost is very less. That is only rupees 10. If that failure is from the field, that cost of replacement will be very high, because that include the name of the company for which the product is there. So next is benefit of DFMEA. DFMEA increase the reliability of the product. It increase the quality of the product. It increase the safety. It also enhance the customer satisfaction. It is important for cost saving. It also decrease the development lead time, warranty cost reduced, and waste reduction is there. So that is the key benefits of the DFMEA. Types of DFMEA, we can have three types of DFMEA. One is system DFMEA, system FMEA. Next is second is design FMEA, and third one is process FMEA. System FMEA means if we talk about a bike is a system which is the assembly of the different products. So if we do the FMEA, failure mode and effect analysis for a complete system, that is called system FMEA. Design FMEA is basically concentrated on the part. Like if we talk about a bike is having several parts, and if I take one part only and do the FMEA of that part, that is called design FMEA. Next is process FMEA. Now, if we are having a part that will be manufactured with the process, so to analyze, to establish, or to make our process foolproof, we have to do the process FMEA. So three type of FMEA is there: system, design, and process. Where we can use our FMEA. FMEA can be used in product definition, that is design FMEA. It can be used in process failure mode and effect analysis, that is process DFMEA. And third, last one is manufacturing, work instructions, process monitoring, and Six Sigma FMEA. So here these are the fields where we can use FMEA. When to create a DFMEA, that is when we need to make a DFMEA. First case is in case of new design, new technology, new process, DFMEA will be there, FMEA will be there. Case 2, modification of existing design or process or use in new environment. Third, for the design responsible engineers. So these are the various cases. Input and outputs to DFMEA. Input required for DFMEA is requirement from customer, corporate, regulatory requirements, system design specifications, quality function deployment, QFD require inputs, history, performance, information, benchmarking data, PPD, targets, P diagram, ideal functions as functions, error state. So these are the various inputs for our DFMEA. And outputs means what should be the DVP, that is design validation testing requirement for the product, robustness check sheet, critical and significant characteristics, system, subsystem, component design specifications, validation criteria, safety sign-offs, control plans. These are the outputs of the DFMEA. Our DFMEA and process PFMEA both are interlinked with each other. First, we will do DFMEA for a product, and DFMEA includes the boundary diagrams, process parameter diagram, that is known as P diagrams, and design verification plans and reports, DVP reports, are also generated from the DFMEA. Now let's talk about boundary diagram. A boundary diagram is the graphical illustration of the relationship between subsystems, assemblies, subassemblies, and components. For example, let's discuss about the boundary diagram of this ignition switch cum steering lock. This ignition switch is our main system for which we are doing the DFMEA. So it our ignition system is interacted with the user. So in that box, we have to write all the parts of our ignition lock, like key, ignition, lock barrel assembly, body, spring torsion, actuator. These are the various parts of our ignition lock. So it has to interact with the user by with physical. So physical interaction is represented by solid line. Energy and information interaction can be represented by this dotted line. Data transfer will be this blue line, and external input will be represented by this dotted line. So now we are if we all know that if we want to operate the ignition lock, we have to insert the key in this ignition lock. Then we have to rotate the key from on to off or from off to lock. So that means user has to interact with the lock physically, as well as energy transfer is also there. That is motion transfer is there. So two lines will be there. So in this way, we can make whole boundary diagram to analyze our system. And we also have to do analysis about the various external factors for which our system needs to be communicated. That is environment, steering column. These are the outer components of our system. Next is P diagram. P diagram is also known as parameter diagram, and it is created prior to start of design DFMEA. It is used to analyze input and output noise factors, control factors that are that can affect the performance of desired ideal functions, minimize error state. So let's take the example of P diagram. So this is our if this is our system. So we have to consider all the noises. Noises means disturbance for our system. First noise is piece-to-piece variation. Second noise is interaction with other systems. Third noise is customer uses, then environment, then degradation over time. These are the five type of noises that can affect our system. In left side, we have to write all the inputs. In right side, we have to write all the ideal functions. At the bottom, there are control factors, that is to control these noises and to achieve all the inputs. What kind of controls we require in our system. Now, our system is also having errors. So all kind of errors that can be there in our system is written at the bottom of the P diagram. So this P diagram will derive whole DFMEA of the product. Now, various steps of DFMEA. First step, planning and preparation. Planning and preparation includes where we have to do the DFMEA. First of all, engineering location, where we have to start the activity of DFMEA. Next is customer name for which we are doing the DFMEA. Suppose I take the example of my product, that is ignition switch cum steering lock, this one. So it is its engineering location is Minda Corporation Limited, Noida, and customer name customer for which we are doing DFMEA is Bajaj Auto Limited. Model year, then DFMEA start date, DFMEA revision date, cross function team, which team is involved in doing DFMEA design, QE, quality engineering lab, testing lab, VD, vendor development team, PMG, project management team. So next is DFMEA responsibility, DFMEA ID number. So this is the planning and preparation for the DFMEA. This is first step. In second step is the structural analysis. Structural analysis includes the focus element over focus element, and in the left side we have the next higher level, and in the right side next lower level. Now, for example, in if we do the structural analysis of ignition lock, so ignition switch comes steering lock. This will be our focus element, and on the left side to which it is assembled at vehicle end, that is to on off the vehicle lock steering and open the seat lever through the cable. So this will become the next higher level for our ignition switch cum steering lock. And in the right side we have to write down all the parts of our ignition lock, that is actuator, body, etc., etc. So like this we can do the structural analysis. Next is functional analysis. Functional analysis means in the center we have to write all the functions of our system, that is focus element functions and requirements. So what should be the function of, for example, uh, for ignition switch, what should be the function? It should mount, it should be easy to mount on the vehicle. And in the left side we have to write the next higher level function, that is which should match with the panel on vehicle. And in the right side, which thing is responsible for this mounting, that is our main body mounting holes should match with the holes of the mounting on vehicle. Means if we want to make the easy assembly, easy mounting of our switch on the vehicle, then vehicle panel should match with the mounting holes for the on the screw on the ignition switch. So like this way we do the functional analysis. Then is the failure analysis. Now, first of all, what is failure? Failure is anything that the way our component can fail. So, in failure analysis, we have to focus on failure of the element. Like in our switch is difficult to mount on the vehicle. We are talking about mounting of the vehicle. So, what should be the failure mode? Failure mode is switch is difficult to mount on the vehicle. Now, by considering this failure mode in our mind, what should be the effect of that failure? That is failure effect. Failure effect means if our switch is not able to mount on the vehicle, then our customer will get dissatisfied and primary function will be failed. So here you can see the severity. Severity means it is the severity of, you can say that it is the negative impact of the failure mode, or you can say the effect of the failure mode. Right in the right side, there is failure caused of the next lower element or characteristics. Mounting, that is mounting hole dimension of switch is not matching with the vehicle panel. Now, what should be restricting the easy mounting of vehicle? That is, if our mounting holes is not matching with the with the panel of the vehicle, then it will not get easily assembled on the switch and customer will get dissatisfied, and severity level of this is 8. So how we can decide the severity level? So we have a severity table. Severity table starts from 1 to moving up to 10. If the severity of that failure is very low, that is, then we have to give the rating 1. If the severity is low, that is moderate failure, slightly objectionable appearance failure, sound, vibration, harshness. These kind of failures, if there are these kind of failures, then severity will be 2 or 3. Then moderately low, that is loss of secondary function, degradation of secondary function. Then severity will be 4, 5, or 6. Severity will be high if there is loss of primary function or degradation of primary function. Then severity will be 7 and 8. Now, if I talk about our failure mode, that is which is difficult to mount on vehicle, that is it will be the loss of the primary function. If there is loss of primary function, then severity will be 7 or 8. So we put the severity 8 to this to our product. So like this way, if the severity is very high, that is there is chances of death, or you can say that health or health hazard to the user, then severity will be 9 or 10. Next is risk analysis. In risk analysis, we do the prevention and detections. Risk analysis means if there is failure, then how we can prevent that failure and how we can detect that failure. In risk analysis, we have to see about current prevention controls and current detection controls. Now, if our failure mode is switch is difficult to mount on the vehicles. Now, if the switch is not able to mount on the vehicles, then mounting hole dimensions should be checked properly. That is first prevention control. Second, mounting hole position and dimensions with tolerance specified as SE dimension in assembly drawing. That means we put the mounting hole dimensions as special dimensions, and it is clearly mentioned in our drawing. That are the two prevention controls for the difficult mounting of vehicles. If we check every part before the assembly of the before the assembly on component, then there is very less chances of this failure. So we, according to that, we have to give the occurrence reading. Occurrence table will be on the next slide. And then detection, mounting hole dimension and position taken from customer drawing. So how we can check that one? With the help of dimensional check. Mounting hole position and dimension with tolerance specified in drawing. How we can check that mounting hole position, mounting hole dia, that is with the help that is mentioned in the drawing. So we have to check that part dimensionally. So dimensional check will be there. So these are the two detection controls, and accordingly we assign the occurrence and detection numbers. So how we can decide the occurrence? If the occurrence, that is chances of failure, is extremely low, then occurrence number will be 1. If it is very low, occurrence number is 2, then low for 3. Okay. Like this, we can, if the chances of occurrence is very high, so write the number 10 at that. So this is our detection table. In detection table, that means how we can prevent or how we can detect the failure. How frequently we can detect the failure. If the frequency of detection of failure is very high, then the rating is 1, 2, or 3, 3 or 4, according to the various conditions like degradation testing. For, for that degradation testing, we have to write 2. For test to failure, we have to write 3. For pass fail testing, we have to write 4. So this is the detection table. So according to detection table and occurrence table, we assign the we assign the number 3 and 2 for the occurrence of this failure, and detection also we decide the 3 and 2. Next is the DFME AP. DFME AP is the action plan, action priority table. According to the severity number, occurrence number, and detection number. Like in our DFMEA, severity number is 8, detection is occurrence is 3, detection is 3. So we have to move to the action priority number, action priority table. severity. If severity 8, so A7 and 8 lies here. So these 1, 2, 3, 4, 4 rows are applicable for the severity number. We are having 8 number, 8 severity. So either we can move in this line, this line, this line, and this line. Now occurrence is 3, 2, 3. So this column will be assigned accordingly. And in the last detection, detection is also 3. So detection in 7, 8, detection 2, 3, 2, 4. So this will be the row again. So this is our action priority number, that is L. L means low priority. Low, L means low, M means medium, and high means high priority. So low priority means there is no action required for our failure. That means if we are choosing that switch can be difficult to mount on the vehicle. So by we have if we have proper detections, proper control, proper dimensional check, then there are very less chances of that failure. So if the chances of failure is low, then no further action is required. That means our product can be worked fine. Next step is optimization. Optimization, the purpose of optimization step is to reduce the risk of product design failure. Now, if DFME AP is medium, then we need to have DFMEA preventive action. If DFMEA preventive action is not necessary for medium and low action priority numbers. If the action priority number is high, then there should be a prevention action for that failure. Then there should be a detection action for that failure. We have to assign the responsibility to reduce that failure to someone. Also, we have to set the target date. Then we have to set the status. Then action taken with the pointer to evidence means we have to take the action and we have to write here what action we assign we do for that failure for high priority action for high priority action number. And then again we have to assign the severity, occurrence number, detection number, and if the DFME AP of the revised failure is low, then our DFME is completed. Next is tolerance stack up. So tolerance, we all know that tolerance is the limit variation on the dimension. So we are having different kind of tolerances. One is the linear tolerance, geometric tolerance, then form tolerance, orientation tolerance, location tolerance, size tolerance. So you can guide your students about the calculation of tolerance and stack up of tolerance as well. Now, stack up means calculation of the required dimensions. Suppose I took one examples here. From 1 to 2, dimension is 1 plus minus 0.05. From 2 to 3, it is 1.1 plus minus 0.5. And from 3 to 4, it is 1 plus minus 0.05. Then what should be the total length of this product, or what should be the tolerance on this total length? The total length, mean dimension, nominal dimension is 1, 1.5, and 1. So we just add those dimensions and then we have to add all the tolerances. So total is 1 plus 1.5 plus 1, that is 3.5, and tolerance on this is plus minus 0.05. So like this way, you can do the tolerance stack ups. Now drawbacks of the tolerance. As we know that any component cannot be made with on the mean dimension, mean value. So there should be always a permissible tolerance on for any dimension. Let's talk about a shaft like this, a shaft and a hole. If we take the example of this, suppose the diameter of the shaft is 10 plus minus zero point 0.1 mm, and diameter of the hole in which this shaft is have to fit that has dimension 10 plus 0.05, and shaft diameter is 10 minus 0.1 tolerance is there. So this is the tolerance range on the shaft, and this is the tolerance range on the hole. So by this way, we can fit the shaft in this hole. So always the tolerance zone on the shaft will be less as compared to tolerance zone on the hole. So only then our shaft can be fitted inside the hole. Now there are some drawbacks. Like if there is main dimension, if there is upper limit of dimension is 16 and lower limit is 14, then our this will be our tolerance zone on the lower side. This will be the tolerance zone on the higher side. So our components can be made like this. If we check the dimension on the left side and right side, then both dimensions are correct. But if we see the shape of the component, that is not correct. So this is the main drawback. Also, if we talk about the cylinder, this is the minimum range and this is the maximum range. Our cylinder can be made like this, it can be made like this, it can be made like this. So we cannot say that direct tolerance, that is dia plus minus tolerance. So there are some generation of shapes like this. To overcome these drawbacks, we have to do the geometric tolerancing. Geometric tolerance is the uh, is having different forms, profiles, orientation, locations, and runouts. Definition. Its definition is geometric. GD&T is the symbolic language used to describe the geometry and allowable variation of the part in engineering drawing. And its importance is the provide clear specification of the part and assembly, ensuring the functionality and interchangeability and quality. So it is widely used in manufacturing, design, quality controls, and assembly process. Now, GD&T is the tolerance over tolerances. Now let's take the example of this square, this rectangle. On the height, we have minimum limit is 14 and upper limit is 14.6. Now, the overall range of the tolerance is 0.6. But at the top of the side, we mentioned this one, this geometric tolerance symbol. This is geometric tolerance symbol, and this is the geometric tolerance value. Now, the various symbols for straightness, we have to use this symbol. For flatness, this will be a symbol: circularity, cylindricity, profile, surface, angularity, perpendicularity, parallelism, position tolerance, concentricity, symmetry. So these are the various symbols that GD&T use in our engineering system. Now, our lower limit is 14, upper limit is 14.6. Our component can be made like this, but the flatness of this surface will vary only in 0.3. That means we provide additional control on the flatness of the component. Next is the use of cylindricity. So this is the symbol of cylindricity. Now, as I told you that if we have only linear tolerance on the dimensions with minimum and maximum limit, the shapes can be like this, and like this. But if we apply additional tolerance of additional geometric tolerance, then thus variation of the shape can be controlled to a large extent, because now the lower limit of the dia is 17.8 and upper limit is 18.2. That means at suppose left side, in the left side our diameter can be 18.2, which is correct, and in left side if the diameter is 17.8, then it is also correct. But the shape of the cylinder will can be like this, or it can be like this, or it can be like this. So if we apply the additional tolerance, that is cylindricity, then we have restrict the variation of the shape of cylinder. So now the shape can be restricted to this one. Next is position tolerance. So position tolerance means it is the variation of the position of a component. Now for that we have to do datums, various kind of datums, and it is the symbol of the position tolerance. Next step of the product development life cycle is marketing, and at the last it is the product launch. So marketing person will do the marketing for the product, and then at the last we launch the product. So this is the complete product development life cycles. So that's it from my side. If you have any question, then we can discuss.
Dear participants, any question from your side? Any question from your side?
So thank you very much, Dr. Gurupej.
Thank you, sir. Thank you for this wonderful session. It was great session, sir. Dear participants, we are sincerely apologize for the technical interruption during the session due to the network issue on the expert side. We truly appreciate your patience and understanding. Thank you, sir. Thank you, sir. Thank you. Dear audience, the first session of tomorrow will be start at 2 p.m. Kindly join on the time. Are you listening me? Participants, please. Okay. Okay, thank you, all of you. We will meet tomorrow at 2 p.m. Thank you.